Welcome to topology class. Today we will discuss about accumulation point of a subset. Accumulation point of a subset. 2.7 definition. We are starting with the definition itself. I know you know the definition of accumulation point from your real analysis class. So let us see, is there any difference between the definition of these two? So let capital A be a subset of a topological space X and Y belongs to X. Then Y is said to be an accumulation point. Of A if every open set containing Y contain at least one point of A other than Y. One point of A other than Y. So meaning is like this. You got a topological space. Okay, X top. Now you got a subset here. Suppose this is going to be a subset. Okay. Now you got a point here, somewhere here. Suppose this is a point. Now this point is said to be a accumulation point of your set A. This is your set A. Now Y is said to be an accumulation point of A if you take an open set containing Y. Okay, take open sets which containing Y. So take another. This way. Now we take open sets which containing Y. That means some members in your tau which containing Y. So these all are going to be open sets in Y. Now if these open sets which containing Y contains at least one point of A other than Y, then this Y is said to be an accumulation point. Okay, let us see one example. First example, let X be set ABC, right? And A subset of X. Sorry, first one we want to define the topology also, right? So let X be ABC and tau be the discrete topology. What was discrete topology? Discrete topology, another name is power set topology. So this topology contains all the subsets of C, or that is this T is equal to, what are the set? X is there, empty set is there, Singleton A is the singleton B, C, then AB, then AC, then BC. Everything 1, 2, 3, 4, 5, 6, 7, 8. Okay, these are the elements of the topology. Now you consider A subset of X as A equal to AC. I'm taking as AC. Okay. Now see, previously I have drawn Y belongs to this A only I have took, but no need that Y should belongs to A. Y can be somewhere here also. This Y value, I have taken a point now. That point may contain here also. Does not belongs to A also possible. So in this case, what are the possibilities for the accumulation point? Now the possibilities for accumulation points are what are they? Either should be A, B or C. Only three members now. But these three points will not form a will not form a accumulation points. What's the reason? Suppose A is going to be an accumulation point, then by definition every open set which containing A should contain points other than A from A, right? That means any open set containing A should contain C, right? But we are having an open set here as singleton A, which does not contain C. Same way, if B is an accumulation point, then every every open set containing B should contain a point other than B from A. That means every open set containing B should contain A or C. But we are having an open set here B, which does not contain any of these members. So B cannot be an accumulation point. In the same way, when you are taking C, we are having a singleton C here. This is an open set which does not contain any of the members other than C from A. So in this case, these A, B, C are not going to be an accumulation point of this subset. So in brief, we can write like this. In discrete topology, no point is going to be an accumulation point of any set. That is in a discrete space, discrete space means a space with a discrete topology. No point is an accumulation point of any set. No point is an accumulation point of any set. Second one, in an indiscrete space, a point Y is an accumulation point of any set A, provided A contains at least one point other than y. A contains a point other than y. So here what will happen in discrete space. In discrete space means we are having, suppose x equal to ABC as we have taken, and tau in discrete topology. In discrete topology. So what was that? Tau means it will contain empty set and the entire set alone. Now you take your A. A should contain at least any set A provided A contains at least one point other than Y. Okay, so we will say that if you're putting AC as before you have taken, now we want to find accumulation point of A. Then accumulation point possibilities are A, B or C. Then A is an accumulation point. What's the reason? A is an accumulation point. The reason is that you take open set containing A. So here only open set containing A is X alone. Now X contain C also, right? So A is an accumulation point. Similarly, what about B? B is an accumulation point. You take an open set containing B. Again, we should take X alone. So that open set also contain, we want to say that at least one point, but when you're taking B, our open set will contain 2 points of A, right? Now what about C? When you're taking C, take an open set containing C, again it will result X. So that will contain A also, a point other than C from A. So here A is an accumulation point, B and C are also accumulation points. Also accumulation points. Reason is since the only open sets is X alone. Open set, we can say that containing A, B or C is X alone. That's why in discrete topology, Y is an accumulation point of a set A provided the set contains at least one point other than Y. Third example. In the usual topology on the real line, in the usual topology on the real line, every real number is an accumulation point of the set of rational numbers. Set of rational numbers. While, see, it says that you take the real line. Okay, in real line with usual topology. Usual topology means the open sets are going to be open intervals. So lots of intervals like this. Okay, these are going to be the open intervals. Now every real number, you take a real number here. This real number, you take it as Y. Now Y is an accumulation point of a set of rational numbers. Will it be possible? Yes, of course. If you are taking this Y, you take an open set containing y means you will get something like this or something like this. But anyway, next to y, here there should exist rationals, right? So we have studied that rationals are dense in R. So when you are taking a real number, in every open set containing that y should definitely contain rational numbers. So this every real number is a accumulation point of the set of rationals. Fourth one, the set of integers. The set of integers as subset of real number with usual topology has no accumulation point, has no accumulation point, right? What's the reason? You take integers is 0, 1, 2, 3. So I'm putting real line, -1, -2, -10. Now you take any integer and take a neighborhood, okay, or a open set. An open set may come like this also, having radius 1 by 2, right? You're taking 0 and radius 1 by 2, then this open set definitely contain no integers except this 0, right? So 0 is not an accumulation point. Similarly, you can take 1, take the radius 1 by 4. 2, you take the radius, again 1 by 4. Anyway, less than 1, that will work. So, the set of integers as a subset of real number with usual topology has no accumulation point. 2.8 definition. We will say that derived set. Let capital A be a subset of a space, be a subset of a space X, then the derived set of A denoted by A dash is the set of all accumulation points of A, set of all accumulation points of A in X. So when you're having a set and in a topological space, a subset, then collect all the accumulation points of that set. Now this set is called a derived set and we will denote it as A dash. So A dash of integers is empty, right? So 2.9 theorem. For a subset A of a space X, for a subset A of a space X, comma, A closure is equal to A union A dash. A closure is equal to A union A dash. Of course, in your real analysis class, you have studied this as the definition of A closure. But here we have studied A closure as the intersection of all topological spaces which containing A. Sorry, intersection of all closed sets which containing A. So proof of this. First we prove that A union A dash is a closed set. So first of all we will prove that this is a closed set. For this, what we will prove is its complement is open. For this, we prove X minus A union A dash is open, that is a neighborhood of each of its points. This we have seen that in order to prove something is open, it is enough to prove that it's a neighborhood of each of its points. So what do we want to do? We want to take a point from X minus A union A dash. So let Y belongs to X minus A union A dash. And we want to prove that there exists an open set completely contained inside X minus A union A dash of Y. Then Y does not belongs to A union A dash, which implies Y is not an accumulation point, right? Y is not an accumulation point, which implies there exists an open set V containing Y. See, whenever it's an accumulation point means every neighborhood of Y should contain points from this set. But Y is not an accumulation point means there exists at least one neighborhood open set V containing Y such that this open set does not contain any points from this, right? So V containing Y such that V contains no points of A, right? X minus this, so definitely it does not contain points of A except possibly or Y alone, right? But Y does not belongs to A. What will happen if Y belongs to A? Then it's a contradiction, right? So we have A intersection with V is empty, right? We claim that A dash intersection V is also empty. So whenever we are proving these two, A intersection V and A intersection V dash are empty means V does not belongs to A union A dash we can have. That implies this V belongs to X minus A union A dash. So we will get that open set. That's why we are proceeding like this. Is also empty. For let Z belongs to A dash intersection with V. Then V is an open set. Containing Z. V is an open set containing Z, which is an accumulation point of A. which is an accumulation point of A, right? Because Z belongs to A dash intersection V. That means Z belongs to A dash and Z belongs to V. Now V is an open set containing Z, and Z belongs to A dash implies Z is an accumulation point of A. Therefore, what will happen? Therefore, V intersection A is not empty, right? Because this Z belongs to V and Z is an accumulation point. And Z is an accumulation point means it should have non-empty intersection with every open set containing this point, right? So V intersection A is non-empty. Now which is a contradiction, right? Which is a contradiction. Since we are taken, so what you are having is A dash intersection V is also empty, and hence what you are having is V is contained in X minus A union A dash. See, we have seen that V does not belongs to A and V does not belongs to V intersection A is empty and V intersection A dash is empty. So V intersection A union A dash is empty. That means V is contained in complement of A union A dash. That is V is contained in X minus A union A dash, which implies X minus A union A dash is open, which implies A union A dash is closed, right? And clearly it contain A, right? Now A union A dash is a closed set which containing A, which implies A closure going to be the intersection of all closed set which containing A. Now this is a closed set, so A closure should be contained in A union A dash, right? So we have got one way of the inequality, right? What should do next? We want to get the other way inclusion. For the other way inclusion, namely, what do we want to prove? A union A dash is contained in A closure, right? It suffices to show that A dash is contained in A closure. What's the reason? Since A is contained in A closure, here the other set is A dash. So once we are proving that A dash is contained in A closure, then A union A dash also belongs to A closure. Since the bracket we can write, since we already have A belongs to A is contained in A closure. So let Y belongs to A dash. So we want to prove A dash is contained in A closure. So let some Y belongs to A dash. If this Y does not belongs to A closure, what will happen? Then Y belongs to X minus A closure, right? Since A closure is closed, X minus A closure is open, right? Which is an open set. Now Y belongs to A dash is an accumulation point, right? But Y is an accumulation point but Y is an accumulation point of A, right? So what will happen? This X minus A closure should have intersection A cannot be empty, right? X minus A closure intersection A cannot be empty. Now which is a contradiction, right? Because A is contained in A closure. So X minus A closure does not contain A, right? So this intersection with A should be always empty only, which is a contradiction, which is a contradiction since X minus A closure is contained in X minus A. So our conclusion is Y belongs to A closure, which implies A union A dash is contained in A closure. Call this as equation B. Now from A and B, the result follows, right? Now from A and B, we get A closure is equal to A union A dash. Okay, so we have proved the theorem. So in today's class, we have discussed about what's an accumulation point, some examples of accumulation points, and one theorem. See, accumulation point, definition, some examples, now derived set definition and a theorem. Okay, so hope you understood today's class. So I'm winding up the sessions here. Thank you for your patient listening. Thank you.